Yeah, I just don't have that. Like, that was my bag. Why did Okay, actually, I want a new one so that I don't need this part. All right, here we go. You probably know, but the doing the lab is like a skill, so you really should do the lab. So I think everyone in here is doing the lab, but just make sure that taking someone else's data, that would be considered cheating. So I don't think that's happening, but just know that you should do the lab yourself. Okay, so this mass is what you actually measured. Okay. We calculated that we needed about 0.31 grams. So I'm going to go with 0.31 grams, but you should use the number that you actually wrote down, okay? This won't work out if, like, you should use the number that you actually recorded, okay? Our scales can give us 2 decimal places, that is 2 sig figs. So at the end, we should have 2 decimal places, or 2 sig figs, excuse me, 2 sig figs. All right, the first step we need to do is to find the moles of KHP. So we need to take grams and divide by the molar mass, and that will give us the moles of KHP. So we need to find the molar mass of KHP. In the instructions that we use, this is KHP. KHP is an abbreviation. This is not the formula. KHP is, oh, they even have the name? Okay, well, there's a name for it. It's like potassium, hydrogen, phosphate, something like that. I don't know if it's that because there's no phosphate, so. Phthalate, it's phthalate. I don't know what that is. This must be the phthalate. Okay. All right, so we have, this is KHP. So you would have to say, oh, there's how many carbons, how many oxygens, how many potassiums, hydrogens, but they have given you the molar mass. This is the molar mass, okay? So you take this number, divide by 204.22 grams per mole. That's how many grams it takes to get to 1 mole for this compound. If I do that on my calculator, let's see if we can do that really quick. So 0.31 divided by 204.22. See, it's a very small number. That's what we expect. These are intermediate calculations, so it is okay if you use more than 2 decimal places, or 2 sig figs, okay? When you get to your final answer, you should round to 2 sig figs. But if you keep more than 2 sig figs for intermediate calculations, that is okay. Okay, so just keep that in mind. Usually we do that. We keep as many as we usually. So Alex says 2 beyond. So maybe I'll do that. 1 point. This is 8. Around to 2 beyond. All right. So then initial and final volume is something that is from the lab. When you did the lab, what was your initial volume? What was your final volume? And then the volume is the final volume minus the initial volume. Final minus initial. That will give you the volume of sodium hydroxide that you actually used. Okay, and this should be in milliliters. I think most people use between 10 and 20, in that ballpark. So I'm going to use 15. That's right in the middle. If I use the burette, I should get 2 decimal places. So in all of these, I'm looking for. It doesn't have to be 0, 0. It has to have 2 decimal places. Okay. Then the next thing is we have to figure out moles of NaOH. So moles of NaOH is the same as moles of KHP. That's because this KHP molecule has this hydrogen that we can titrate with sodium hydroxide, and that's how we're counting. We're counting how many sodium hydroxides do we need for the KHP that we measured, it's a 1-to-1 ratio. So if I have this many KHPs, I'll have the same amount of NaOHs. So that's moles of KHP. Oh, so this box is the same. And that's why we want that very light pink color, because at that light pink color of our titration, it means we have equal amounts of H plus and OH minus. So that's why that works. Molarity is moles divided by liters. Are we okay? We're okay? Okay. So milliliters this is milliliters. We need it to be liters. So to get to liters, take milliliters, divide by 1,000, because there's 1,000 milliliters per liter. That will give us liters. So, or I'm going to move my decimal place 1, 2, 3 to the left. I'm going to write the calculation. You should write the number in this box. So 15 liter, oh, it's not 15 liters, 0.015 liters, and moles goes on the top. This is the moles, 0.001518. So moles divided by liters gives me the concentration, which is moles over liters. That's the unit of molarity.
Is it 2 sig figs?
Yes. So here it's a final calculation. You would want to put 2 sig figs. Yes. 2 sig figs here. You should have done this at least 3 times. Or if you did it more, take your best trials. Find the average. Oh, I didn't tell you, but this was in the teacher notes. I forgot. If you ever do an experiment in science where you decide that your data wasn't great, like I know I added at least 5 extra milliliters, I shouldn't use that as a calculation. Don't erase your data, just do a dash through it so that we can still see that you did the experiment. And you're not like hiding data. You're just showing that, this didn't work. And this is why it didn't work. I'm using my rationale to not use it towards my calculation. There was an error, but I'm not getting rid of the data. I'm not hiding anything. Okay. All right. So you should have your average. This is concentration of NaOH. Remember, when I measured it out, it was about 0.1. So I put 4 grams of sodium hydroxide into 1 liter, and that, according to my calculator, is 0.1 molar. So you should get pretty close to 0.1 molar. A lot of the class yesterday was getting like 0.09 or 0.08. So, that's quite close to 0.1, so that's good. And it's also good that you do the standardization so that you get the exact concentration. What's interesting?
I got one at 0.09, one at 0.093, and one at 0.089.
Okay, so all close.
It equals all 0.0.
Okay.
It's just 2 away from 0.093. It's 2 away.
Okay, so that's very accurate data. You're very close. Close window, good.
That's what mine should
be. Oh, that's what yours should be like. Oh, yes. Because what was your... Do you just divide this by KHP first? Is that what you... Okay. Yes, that happened last year. I thought that wasn't going to happen this year because it's in the instructions.
I thought I used that.
You thought... No, I'm sorry. Okay, and that's why we're going over it, because there's lots of numbers going all over. And this is quantitative chemistry, so if this is enjoyable for you, this is something that chemists do. They figure out how much of something is in something, or if they're doing a batch, they're making a batch of something. How pure is it? Something like that. So this is real life. So this is real life. This is kind of exciting. I like this part. I don't like doing the lab. Okay, so the next part is we were titrating vinegar. So you diluted your vinegar, you took some vinegar dilution and you titrated it. So these are from the lab. You should have your initial and your final volume. And then again, to find the volume that you use of sodium hydroxide, you're going to take final minus initial. And that's going to be the amount that you actually used. Then you're trying to find moles. When I find moles, moles is little n. N is concentration times volume. So I need to use the concentration of sodium hydroxide that I got here, the average. So we'll use Simon's. So yours was 0.091, 2 sig figs. And how much did you use here? What was your answer for volume?
11.65.
So you need to take that and make it into a decimal or a liters. It needs to be molarity times liters, or moles per liter times by liters. That will give us moles. Okay, that's what we're looking for. If you're not sure what to do, you can always look at units and make sure that units will cancel out. So this one was moles per liter. This one is, you said 11 point something, so 0.1165. Okay, good. 2 decimal places. Good. So these ones have 2 decimal places. 2 decimal places. Okay, so then this one is an intermediate step. I would leave more than 2. Okay, let's do that. So again, you should be using your numbers. You understand that? Great. So this was milliliters. Oops, 6.5. So 0.091 times by 0.01165. This is intermediate, so I would probably put 4 sig figs just because it's intermediate. Yes, so you don't round too early, like in Alex when you don't want to round too early. So that's how many moles of sodium hydroxide that Simon used. Okay, let's come back to this box. This one's tricky. Moles of acetic acid equals moles of sodium hydroxide. This acid is monoprotic, so that means it's a 1-to-1 ratio. Not all acids are 1-to-1, so if you do a different titration, you need to check. This one's 1-to-1, so for every sodium hydroxide, I have a vinegar. And this is moles, and I don't have to put units because it's at the top. Moles is equal to moles of NaOH. Okay, I'm going to pause here. Yes, Wesley.
So I got 9.168 E negative minus 4.
Times 10 to the, so you have, tell me again, 9 point what?
168
Times 10 to the?
Okay.
Times 10 to the what? Negative 4, okay.
Okay, that's
1, 2, 3, 4. And so, oh, okay. And so then Simon got 10 and you got 9. So you are on the same order of magnitude. 11 is also, like if you have 0.0011, very similar. Like this one could round to 11. So those are in the same ballpark. That's good to think about. Does this make sense? Perfect. Okay, this is a tricky box. This is dependent on how you diluted your sample. So I'm going to show you a few different ways with this side of the paper. So we're looking at how much vinegar. How much vinegar was in your sample? Okay, so in class, I took 10 milliliters of vinegar. I diluted it to 100 milliliters. I had a 100 milliliter flask and I diluted it to 100 milliliters. So this is 100 milliliters of vinegar in 100 milliliters. Okay. And then I'm going to multiply. I took 10 milliliters of the diluted sample. So, this gives me 1 milliliter. I used a pipette, so I should get 2 decimal places. That's 360. Oops, there we go. 1 milliliter. Some of us might have followed the book. The book instructions said take 20 milliliters of vinegar, dilute to 100 milliliters, take 10 milliliters of that sample. If you did that, then you'll get a sample of vinegar in your titration that's about 2 milliliters. Okay. If you use a different flask, then you change this number. So if you take 10 milliliters of vinegar and you put it into a 50 milliliter flask, and then you take 10 milliliters of this sample, 10 times 10 is 100, divided by 5, 0.5. That'll be 0.5 milliliters. Is that right? 10 times 10, it should be bigger. 5 divided by 50, 2. My calculator says it's 2.
I didn't see the 0. Sorry.
Oh, no, that's okay. Thank you for double checking. Yes. Molarity does not equal, let's see.
It'll be the same number, but it doesn't.
So let's do it like that. So if I had 1 milliliter of vinegar, so you put what this is going to be different depending on your dilution, okay? If you use 1 milliliter, you should have used about 10 to 12 milliliters to titrate. It will be about 20 milliliters to titrate if your sample was 2. So that's another way you can think about. Does this make sense? Okay. So if you're using about 10, your sample is probably about 1 milliliter of vinegar. Okay. So molarity is moles divided by volume in liters. So here, moles is this number, 0.001060, divided by liters, this volume. Move the decimal 1, 2, 3, so 0.001 liters, this is moles, so then we'll get molarity. And this one you would want to have 2, let's see, this has 4, this one up here had 2, and we had to use that here, so that we can only have 2 sig figs. 2 sig figs. Okay. So I don't think, I think that means the decimal place changes, Chloe. Is that right?
So we got 1.06.
Okay. So 1.06. And then 1.1 because we need 2 sig figs. All right, that means average, easy. Okay. Are we okay? Questions? So then you're going to find the average. And I assume we're okay with the average. If you need help with that, then we can do that, but hopefully you got that. All right, the other thing I would do is you should have 3 boxes, at least 3 boxes of moles. I would also find the average for the moles because we're going to use it for question number 2. Okay, so let's pause there for a second. Questions? Okay. The post-lab questions. So we wrote our procedure, that's 4 points. I'm just looking to see that you did that. I think you all did because you did the lab. And then the post-lab questions, this one is, what was your determined concentration of acetic acid? So basically, walk me through, how did you find this number? Oh, let's see, this number. The average acetic acid concentration. You could do like one example calculation. That would be how you do that. So first, take this, divide by 204.22. That's the number of moles that you need. Divide by the volume that you use. Find the average. Then multiply by the volume of sodium hydroxide used for acetic acid. That's the number of moles. Take the moles divided by the volume of vinegar. So that's just do an example calculation. Okay, this one's a little bit different. If the accepted value, so if you go to the store and you buy vinegar, or if you look at the bottle of vinegar in the lab, it tells you the concentrate or the percentage of vinegar. So it's mass percentage. So this question, we're going to do grams of acetic acid
So what was the dilution of water to say?
over the grams of vinegar. So what I'm thinking about when I'm doing this is I have maybe a beaker or a cup with vinegar. Most of that is water or other stuff. There's about 5% that is the acetic acid that we know as that, like that strong smelling acid. Okay, that's what makes vinegar vinegar. But we are not drinking straight. We don't drink vinegar. But when we use that in cooking, we are not using straight vinegar or acetic acid. It's a dilution. Okay, does that make sense? Okay, so this is asking how close to 5% did you get? So the first thing that we are going to do is we're going to take the average number of moles of acetic acid. So that's, we're looking at moles. That is from the average here. So you should have an average number of moles. So take your moles. We need to go to grams. So when we go from moles to grams, good. Multiply by the molar mass, atomic mass. I think it's molecular mass. I'm going to call it molar mass. Of vinegar, you can look that up or you can calculate it. It's 60.05 grams per 1 mole. And that will cancel moles, we'll get grams. So we're looking for grams of acetic acid. That's how we're going to find grams of acetic acid. This average times by 60.05. This should have 2 decimal places, or not 2 decimal places, 2 sig figs. This should have 2 sig figs. This should have 2 sig figs. All right, the next one is we need to convert. We have a volume of vinegar that we use. I'm using 1 milliliter. We need to find that in grams. So we can use the density to go from volume to mass. So this is what I'm going to do. I'm going to take 1 milliliter of vinegar. Okay, I'm going to do like this, 1.00. This is 3 sig figs, okay? Times the density of vinegar, which is 1 gram per milliliter. All this is doing is converting to mass, okay? If I have the volume and I need to get to the mass, I can multiply by the density. Okay, and then if your volume here was 2, then you should use 2. If it was something else, then you should use that something else, okay? So then we should have the grams of acetic acid from the moles and the grams of vinegar from the volume. We converted with the density. Grams over grams, and then it's a percentage. We need to multiply this number by 100 to get a percent, and that will be your percent vinegar. Okay, and that is the answer for number 2. The correct value is 5% compared to yours to 5%.
So for number 2, should we use the average volume?
I would use. Did you? Is it changing?
A little bit.
Use the volume of vinegar that you use, which should be the same every time. Because so this is your sample prep.
Vinegar. I was looking at
Yeah, use this one. Yeah. Okay.
That makes sense.
Yes, Chloe.
So for the first post lab, you want to show me how we found the molarity of the acetic acid?
Yes. I would do an example calculation. Just walk me through one example calculation.
And then for values, about 1.7%.
Yeah, 5% is the actual. 5.2. That's also close. That's awesome. yeah, this lab works pretty well, especially if you're really careful. So that's awesome. Good job. Okay, let's pause here for a minute. Other questions? Okay, if you haven't done this lab, just talk to me and let me know when you're planning to do the lab. So if you haven't already. All right, after this, we are going to talk about chapter 13. We're taking 2 days on chapter 13. I will hand out the note sheet while you are finishing up the lab. Okay, chapter 13 has 8 topics. I don't know how many of them are on this. Probably all. Has 8 topics.
She's very distorted.
It's not.
Is that like this person? Okay, so I'm gonna pull up some notes, chapter 13, day 1 of notes, and I'm also gonna pull up Alex. So, hold on till I do that. So just a reminder that the more of your PI progress you can get done before we study for the final, the better, because your topics have to be open so that you can review them. So just try to get as much of the PI progress as you can done. And we have a So chapter 13, we're just building off of 11 and 12. So you can't forget 11 and 12. We're just adding rules to our game, our organic chemistry game. Okay. So we're going to go through a few slides, and then we'll do some examples and Alex. Let me see if I can find the English. I don't know if I have that anymore. Alright, here we go. So the things that we're adding in chapter 13 are double bonds and triple bonds. So we talked about the end of the name. We tell what's special about this molecule. Chapter 11 and 12 we used A and E, which was just like a boring carbon hydrogen. If we have a double bond, we're going to use E and E. If we have a triple bond, we're going to use Y and E. So that's basically most of what we're going to talk about today. So alkenes are compounds that contain a carbon-carbon double bond. They have this general formula where, so this is a pattern. However many carbons, we have 2 times that many hydrogens. If that's true, then we have 1 double bond. This name comes up in chemicals, so you should start looking for this ENE in chemicals that are around you, maybe on food labels, probably not food labels, but like isoprene, that is a chemical, that's ENE, so that has a double bond in it somewhere, okay? Okay, all right, very good. So another important thing is that this double bond locks the structure. If there's a double bond, the molecule cannot rotate, and so this bond angle is locked in a 120-degree angle, okay? Do you remember what the bond angle is if it's an alkane? No double bond, nothing special? Good, 109.5, good, good. Okay, if it's an alkyne, that means we have a carbon-carbon triple bond, and this is our chemical formula. We have some kind of carbon and hydrogen, 2 times the number of carbons minus 2. We'll get there. If we have a triple bond, the furthest the atoms can be away from each other is 180 degrees, and it's locked into that. The important part is that if we have a triple bond, we need to change the ending of the parent chain to YNE. So pentane becomes pentyne. And that tells you that somewhere in your structure is a triple bond. Okay, so when we add a double bond or a triple bond, that's what we call an unsaturation. We're adding an unsaturation. So a saturated hydrocarbon is an alkane where all of the carbons are full of hydrogens. If we have a double bond, we're starting to replace the hydrogens with bonds. Okay. So that changes the chemical formula. So if you notice that we have 2N minus 2, that means we have 2 unsaturations. We have basically we have 2 double bonds, but it's a triple bond. Okay. Another thing that adds an unsaturation is a ring. So one of the ALEKS topics, you have to look at the chemical formula, and a shortcut is to know that if you have a double bond, you have 1 unsaturation. If you have a triple bond, you have 2 unsaturations. If you have a ring, that's 1 unsaturation. So every one of those, you're going to lose 2 hydrogens compared to an alkane. Okay. Have you heard of unsaturated fats or saturated fats? That's what this is talking about. It's talking about, is the carbon chain full of hydrogens, or is there a double bond or a triple bond? I don't know if we eat triple bonds. Okay, so back to this, we have our parent chain. We're going to look for the longest continuous carbon chain. If we have a double or triple bond, we have to include the triple or double bond in the parent chain. So we have to follow the path that includes the double or triple bond. The prefixes are the same. So what is it? Where is it? What's the number? And then the suffix, now we're going to use the suffix. That's the alkyne or the ENE, that's the suffix. That's telling us, does it have a double bond or a triple bond? Okay. If you take more organic chemistry, there's like a year-long course in college, and you learn even more of these different endings. So if you want to speak chemistry, you could take that class. Let's see. So the numbering is a little bit different. We're going to number so that the double bond or the triple bond is minimized. We want to prioritize the double bond or triple bond. Okay, even if there's a branch, the double bond or triple bond wins. Okay. So for example, this one, the triple bond is closer to this end. So we're going to start from this end so that we prioritize the triple bond. Okay. We're going to start from this end because we're prioritizing the double bond. So prioritize the double or triple bond. If it's a tie, then you can look at the next branch. So if for some reason you have a double bond at both ends, and it doesn't matter which end you start at, go by the first branch. Go back to the other rules. Okay, questions so far? Yes?
If there's a double on the side, triple on the side, will you prioritize them?
Probably. I would prioritize probably the triple bond because that's more special, but I don't know if we'll see that. I hope we do not see that. I don't think that's in our rules, so IUPAC has a rule for everything. Anything that comes up, there will be a rule for it. So even if we don't use it, I'm sure there is a rule for that. So if you really wanted to know, you could probably look it up. So I don't know that one, but I would assume it's the triple bond. Yes. So this is just the rules. The rules are on your sheet in the first box. Okay, so this is just our additional rules. If there's a double or a triple bond, we're going to prioritize the double or triple bond. If there's a side chain, if it's a tie, we're going to prioritize the side with the side chain. The next thing is if we have the double bond or triple bond in the middle or at the end, we're going to specify the first locant of the double or triple bond with a number. And I will show you some examples in ALEKS. It is optional to name the location of the multiple bond if it is in position 1. So if you leave the number off, then that means it must be at the 1 position. Kind of like if you had like ethyl cyclopropane. That means it's at the 1 position. Okay, and then same rules like before. Name the side chains, name the parent alkene or alkyne. We're changing the end of the parent chain to ene or yne. Okay, there's some examples. We're going to go through some examples in ALEKS. The next thing that we need to talk about is the structure of these organic molecules. This is the definition of an isomer. It is a molecule that is different, but it has the same chemical formula. So it has the same atoms. They're just connected differently. Okay, that's an isomer. So both of these have 3 carbons, 7 hydrogens, 1 bromine. Same. The only difference is that the bromine is connected to the end of this molecule, and the bromine is connected to the middle of this molecule. Okay. That affects the chemical properties. So these are different molecules. Even though they have the same chemical formula, the structure makes them different. That's really important. We have to start identifying if the molecule is structurally different, because even if it has the same formula, it will be chemically different. Okay, and there's been some instances of some drugs that have had something similar to this, where they're the same formula, but they're like just a little bit different geometrically, and that gives them different properties, and that's really important. Okay. So that's something that we need to be able to identify. So this is how you decide if it's an isomer, and we'll go through this topic in ALEKS. These are the questions that I ask myself. Do they have the same chemical formula? So that's really tedious, but you need to go through and figure out what is the chemical formula for all 5 molecules on that question. Then you have to also check, as you're going, you can do this, is it a different molecule? There's a lot of ways that ALEKS can rotate the molecule or flip it or bend it, and it is the same molecule. If it's the same molecule, it is not an isomer because it's connected the same. If it's connected the same and it is the same chemical formula, that's just the same molecule. It's not an isomer. If it has the same chemical formula, but it's connected differently, like the Legos are stacked in a different way, that's an isomer. That's what the question is asking. Okay, the last thing that we need to talk about is rigid parts of molecules. Let me pull out a model. Let's look at a few. We'll start with this. So if I have a molecule and it has a single bond, so we'll do hydrogen chloride, HCl. So there's a bond between hydrogen and chlorine. This is modeling a single bond because a single bond is 2 electrons being shared. So I can pretty easily spin this. They're connected, but I can spin that, okay? So you have to know that if there's a single bond, the single bond can easily rotate. We can easily rotate around a single bond. We cannot easily rotate around a double bond. So let me look at this. So if I can do this. a carbon-carbon bond. Decide which one. There's a trick to this one. This one? Okay, so we'll say this is our double bond. So we have a double bond here. So these are sharing 4 electrons. If there's a double bond, this models it pretty well, it can't rotate around that double bond. So the molecule, if there's a double bond, the molecule is locked, okay? And that's really what's going on, okay? If I wanted to spin this bond, I would have to put some energy in, break the bonds, then the molecule could rotate, okay? But right now with the double bond, it can kind of vibrate, but it can't rotate all the way, okay? So we would have, so what you have to do, this should have another, oh, yeah. You have to think about what's happening. You have to think about what's happening with the atoms that are attached to the double bond. Okay, if this can't rotate, then these bonds, the distance between these 2 hydrogens can't get away from each other. Okay. If I have this chlorine, these electrons can't get away from the hydrogen because they're on the same atom. Okay. But if I have something else, if I have a single bond between chlorine and oxygen, and then there's a hydrogen over here. This single bond, the hydrogen can start to spin. Okay? And so that distance can change between the hydrogen and these electrons. That distance can change. Okay? So this is a 3D model. They're going to give you a 2D model, and you have to think about what is happening in 3D space. Okay? Sometimes this is a tricky topic, so this is something that I would practice a lot to make sure that I understand what's going on. If you practice for you practice for a while and it's not making sense, I have some model kits that you can check out and you can build the question that they're asking. You can try to play with it and see what's moving and what's not. And sometimes that can help you. Okay, great. So let's go to Alex. We'll go to chapter 13 and we'll do some of these topics. Okay, let's start with the naming, alkenes and alkynes. So this one just starts right off with branches. So this one we're going to prioritize the triple bond. I always put the number for the triple bond, but it is optional. So I have to include the triple bond in the longest chain. I'm going to start here. So this is going to be 1, 2, 3, 4. So we're using the same stuff that we've already learned, but now with the triple bond. The methyl will be at the 3 position. So this is going to be 3-methyl dash. I'm going to put the 1. There's a 1 Y-ene. So 1 dash. This is butane, but instead of ane, I'm going to put Y-ene. Butane. That's telling me there's a triple bond somewhere in that molecule. The 1 is telling me where that Y-ene is, where the triple bond is. Okay, next one. So I can go this way, 1, 2, or I can go this way, 1, 2. Either way, that's equal. So I'm going to prioritize the branch if it's equal. That's the tiebreaker. So 1, 2. So that's going to be 2-methyl. Oops, 2-methyl. Dash. I do have to put the location if it's not 1. This is also butane, but O dash. E-N-E, butene, E-N-E, there's a double bond. This suffix is telling me there's a double bond, and the 2 is telling me that it's at the 2 position. It starts at the 2 position. Okay, next one. Okay, this one I could go 2 ways. I have to go this way because I have to include the double bond in the main chain. So I'm going to say this is the double bond, the ene, is at the 1 position. The methyl group is going to be at the 2 position. So this is going to be 2-methyl -1 butene. The ene, the double bond, is at the 1 position. Okay, let's check. Let's do one more. Which one do you need? Okay. All right, so this one, I think we just did this one. This one we're gonna go this way, 1, 2, to prioritize the double bond, but also the methyl is right there. So 2 methyl, I can't see. 2 methyl dash, what's after 2 methyl? It's also the 2 ene 2 dash butene. Okay, we already did this one also. We're going to follow this path. This is 2 dash, methyl dash 1 dash butene. Again, the 1, if it's at the 1 position, is optional. I always put that, but that is optional. So this is telling me the ene is at the 1 position, the methyl is at the 2 position, the longest chain is 4. All right, this one is a Y and E. The methyl will be at the 3 position because I want to prioritize the triple bond. So this one is 3 dash methyl dash 1 dash butene. I'm changing the ending to Y and E. The Y and E tells me there's a triple bond. Oops, row 1. What did I miss? Oh, thank you. Spelling. Okay. Yes, go on. Okay, questions? Okay, let's do the next one. Next one, so we're going to do most of the items next time. Naming and drawing linear alkenes with 1 double bond. So this one can go back and forth. Make sure that you draw the correct one. If it says skeletal, draw the one with the sticks. If it says condensed, draw the one with the CHs. Make sure you draw the right one. This says skeletal. It says 4-fluoro 1 pentene. I'm going to draw the parent carbon first. So pentene is 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Another hint is that they're both pointing the same way, so that is an odd number of carbons. If it's pointing opposite ways, it's even number of carbons. The 1 ene, the double bond, is at the 1 position, and then there's a fluoro at the 4 position. 1, 2, 3, 4. This is pointing up, so I'm going to draw the fluoro pointing up as fast as I can up, and then fluorine. Okay, questions on that? So just following the instructions to draw what they say. Okay, let's do, so they go back and forth between naming and drawing. This one we have just a double bond, no branches. 1, 2, 3, 4. So this would be butene or 1 butene. I'm going to put 1 butene. We'll see what happens. The double bond is at the 1 position with 4 carbons. Okay, this one I want to go from the right side because that's going to make the double bond at the 1 position. Prioritize that. So the methyl will be at the 2 position. So this is 2 dash methyl dash 1 dash pentene. So pent means, no, prop. This is propane. 1, 2, 3, propene. Okay. Propane is 3. There's a double bond, so it's E and E. Okay. All right, this one, I'm going to start from the right side also because I want to prioritize a double bond, even though that methyl group is right there. Also, watch out. I've seen a few people who have switched the chlorine group. In their head, they think that's a methyl. Make sure that if you're looking at that, that's a chlorine group. Okay. So our longest carbon chain is, we could go all the way to this carbon. Okay. So let's see. So what we have is fluoro at the 1, 2, 3, 4 position. So this would be 4-fluoro, spell that right, dash, and then we'd have to count this carbon as part of the chain. 1, 2, 3, 4, 5. So that's 10, oh, I guess 1 dash 10T. 4-fluoro dash 1 dash 20. Okay. Question, let's check. Alright, you're getting the hang of that? Okay, let's do another drawing one. Condensed structure. That means we're going to draw the CH stuff. Pentene is 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1 pentene, so it just has to be on the end. Okay, just like before, all of the carbons can only have 4 things connected. So I just added this double bond. I need to fix this carbon needs to have just CH2. This one needs to have CH. So now carbon is connected to 3 bonds and a hydrogen. So 4. Carbon is connected to 2 hydrogens and 2 bonds. 4. You have to go back and do that. That's still one of the most missed questions on the test. If people miss things, that was one of the things. Okay. How are we doing on the naming? Should we do this one? This one's the skeletal structure naming. We're good. What do you want to do? One more of these? Okay. Yep. All right. So this one, they're both pointing down, so it's an odd number. Let's see how many. 1, 2, 3, 4, 5. I'm going to count from this side because I want to reduce the double bond. So that's going to be 1 dash 10 Oops. Okay. 1, 2, 3, 4, 5. All right, this one's a little bit weird. We have to include the double bond, so we have to go through this path. We have to include that. I'm going to prioritize that, so that's going to be 1. This is going to be 2. This is going to be 3. This is going to be 4. So that's a bit weird. I remember from last year, people sometimes count these as both methyl groups, but I can make the path out of that, so make sure you make the longest path. Don't have extra methyls floating around. That could have been part of your path. 1, 2, 3, 4. The fluoro is at the 3 position. The methyl is at the 2 position. So we're going to say 3-fluoro. Make sure you alphabetize the prefixes. 3-fluoro-2-methyl. And then -1-butene. 1, 2, 3, 4. 3-fluoro, 2-methyl, 1-butene. Okay. This one, we have to follow the path that includes the double bond. So I'm going to go this way. 1, 2, 3. So that's going to be propene is my parent structure. And then there's 2 fluoros. There's one at the 2 position and one at the 3 position. So this is going to be 2, 3 dash. There's 2 of them, so don't forget you need prefixes if there's more than one. Oops. 2, 3 dash difluoro dash 1 dash propene. 2, 3 difluoro 1 propene. 1, 2, 3. Okay, lots of little things to remember, but if you can remember all of them and keep them straight, then it's pretty straightforward. Just think of it as like a game. That's not so bad. Okay, let's move forwards from that topic. We're going to talk about 2 more. These are kind of tricky, so we'll go over the rigid structure first. So you're going to get a picture, and you have to remember, if it's across from a double bond, that's going to lock it into place. If there's a single bond somewhere, it could probably rotate around that. Okay, so I just like to go through and look at each of the distances. So they're saying, if I'm looking at this distance between this hydrogen and this oxygen, is there anything in the structure that can allow that distance to change? So what I like to do is, if I have a trapezoid, this trapezoid between the double bond and the arms from the double bond, that is locked into place. So I look for those, okay? So anything, can you see this trapezoid? The double bond is the top of the trapezoid. That is going to be locked. Okay, that's like this one. Where we have the double bond. This is not very, I need to figure out how to connect these. But we have that double bond and then our two branches, and that's locked. It can't rotate. Okay. So anything across from a double bond cannot rotate. Let's see. But this one has a single bond, so it can. So let's erase that one. Oh, so that's not erased. Okay, so let's just go through the bonds. So I see A is asking if these distances can change. Well, this is locked, and this is locked, but there's a single bond in between. So this can rotate, this single bond can spin. So if I have my finger as the spin, and then like the oxygen and the carbon, this oxygen can change distances from hydrogen. Okay, so A can change. So in the box, if it can change, I need to put it in the box. A can change. The next one is B. Can you see this? B is across from a single bond. So this can spin, and that's going to spin the carbon-oxygen bond. Okay, so these can change distances. Okay. This is something this is tricky. So hopefully that makes sense to you. If it doesn't, try for a little bit to try to figure it out. If it's not making sense, come talk to me and I can check you out a model kit and we can build this and see what spins. All right, can you see how C is looking at the oxygen connected to the carbon and the hydrogen connected to the carbon? That is connected to the same atom. So if you're connected to the same atom, you cannot get away from each other, even if you can spin. Okay? So the chlorine hydrogen cannot get away from each other. It's spinning around the bond. Okay. So because it's connected to the same atom, that can't move. D is across from two single bonds. So this one can rotate H and H, and this one can rotate H and H. So D can also change. A, B, and D. Okay, more practice. All right, so this one, we have A. Can you see this trapezoid? The top of the trapezoid is a double bond. That's locked, so that means H to H is locked, so A cannot move. The next one is talking about B. B is across from a single bond. That single bond can rotate, so hydrogen to oxygen, that hydrogen to oxygen distance can also spin. It can change because that bond can spin. The next one is C, which is also across from a single bond. So because this bond can spin, that's going to flip. This can flip down and change C. So let's see. Oops, we have to put it in the box. So C can change, B can change, C can change. What else? D is on the same carbon. Oxygen to oxygen on the same carbon. That cannot change. E. So let's see. Can you see how there's a trapezoid again? You have a double bond at the top of the trapezoid, and that's going to lock in this carbon and hydrogen. So that's going to be not able to move. So only B and C can rotate. Okay. Do you want to do another one of these? Or okay, let's do another one. Okay, this one. So I just go A to the end of the alphabet. Well, let's see what's unmarked. I don't remember this. Oh, so if you need to not see the distances, if that's helpful, you can go back and forth. So A, I'm looking at C to oxygen. Can you see how it's across? We have that trapezoid again. The top of the trapezoid is a double bond, and the bottom of the trapezoid is between the two atoms that are connected to the elements in the double bond. Because that double bond is locked, then I think this is A. A can't move. I think that's A, right? Yeah, okay. B, let's look at B. B, what do you think?
Yes.
I think so, because this one can spin. So this one can spin so that this oxygen can end up where the hydrogen is. So that B can change. So we gotta write that in the box. B, comma. Next one is C. Let's see. There's a few there's a few single bonds here that can rotate. This one can spin. If this spins, it's gonna flip that whole thing. So it can rotate. This can also spin. So that can rotate. So C can change. D is the distance between this oxygen and carbon bond. If we look to the trapezoid, that's a single bond. So that can rotate. So that can spin. So the carbon can end up over where the hydrogen is. So that D is going to change. D. And then let's look at E. E is looking at this oxygen connected to the carbon and the nitrogen connected to the same carbon. If it's connected to the same atom, it cannot get away from each other. So E does not rotate. And that's all the letters. Okay. That's one that I would practice a lot. I feel like after 3 years, I'm pretty good at it, but I've had 3 years of practice. So make sure you practice that one so that you're confident in that one. We have 10 minutes, so let's go to our last topic, and then next time we'll go through. We're going to get through 4 topics today, 4 topics next time. We will have more work time, I think, next time because we won't talk. We'll talk about the pre-lab, but we'll see. We should have more work time next time, hopefully. The next one is identifying constitutional isomers. This is a tedious topic. And this is one, if you understand the saturations and the unsaturations, that can help you. So if I'm looking at the structure, the first thing that I'm going to do is I'm going to write down the chemical formula for each of these. And that's tedious, but that's the best way to do this topic. So if I look at this molecule, remember all the N's in the corners are carbons. So this has 5, 6. Carbon, 6. And then I have to figure out how many hydrogens. I'm just going to write. So this is an N, so it's 3. This one has 3 bonds, so there's 1 here. This one has 2, 2, 2, 2. So let's see. So that's 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12. Okay. And notice that has 1 unsaturation. So 2 N's, 1 unsaturation. No. It only E is a
Well, so like only when it's
So if there's an E, it could be. That's okay. Yeah. Okay, so this first one, I'm just going to look at that, and I see that it's the same molecule. So it cannot be an isomer if it is the same. It's just rotated. Okay, that's like me spinning. I'm still the same person. I just moved my arm. So this one is not an isomer. This one is an alkane. So if you understand saturations, this has no unsaturations. This is going to have more hydrogens. The easiest way to see that is just to write out the chemical formula. 1, 2, 3, 4, 5, 6. Great, we have 6 carbons. So how about hydrogens? We have 3, 2, 2, 2, 2, 3. So 6 on the ends, 7, 8, 9, 10, 11, 12, 13, 14. So no unsaturations. This is the saturated hydrocarbon. Doesn't have the same formula. It has to have the same formula for it to be an isomer. Different formula. Okay, what else one? Not an isomer. It's just rotated. Okay, wrong. Not an isomer. How about this one? Well, we don't know. Let's look. 1, 2, 3, 4, 5, 6 carbons. Okay, we're back to 6 carbons. And then 1, 2, 3 here. 3 hydrogens here. 3 hydrogens here. There's 2 bonds and another bond left. 1 hydrogen. There's 1 hydrogen here. There's 1 hydrogen here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the formula is the same. This is obviously a different molecule because this one has a ring, this one has a double one. Different. So this one would be an isomer. It is a different molecule, but it has the same formula. Those are the 2 things that we have to check. Different connections, same chemical formula. Okay, let's do another one. So same thing, we're going to, this one has one unsaturation. We're gonna count the carbons, 1, 2, 3. We're gonna count the hydrogens. There's 2 here, there's 1 here, there's 1 here, and then there's these ones. 2, 4, 6. And then we have 2 oxygens. Okay, so this molecule, let's just look at it. Is this the same molecule? You have to be careful, but this one looks like the same molecule. Same molecule, not an isomer. Okay, how about this one? We have 1, 2, 3 carbons, C3, and then 2 hydrogens, 2 hydrogens, 2 hydrogens, that's. Oh, that's what's going on. There's only 3 carbons. Okay. Hydrogens, 2, 4, 6 hydrogens, 2 oxygens. So, is this a different molecule? Yes, this one has a ring on the other. So different molecule, same formula. So this one is an isomer. So I'm gonna click the box, isomer. This one down here doesn't have OHs, so it could be a different molecule. This one also looks like a different molecule. Okay. There's a lot of different ways you can flip the molecule, so just make sure that it's a different molecule, not the same molecule bent or rotated. This one, let's look at the chemical structure. We have 3 carbons, 1, 2, 3. We have 3 hydrogens here, none there, 3 here, so that's 6, and 2 oxygens. So this one's also an isomer. It's the same chemical formula, but they're connected differently. They're gonna have different chemical properties, even though it has the same atoms. All right, this one we have 1, 2, 3 carbons. There's 3 hydrogens at this end. There's 2 here. There's 1 here, so that's also 6. And then oxygens, we have 2 oxygens. So this is another example of an isomer. These are geometric isomers. Okay. I guess check the book. We have 5 minutes left. Do you want to go over more examples of anything, or do you want to just work for the last 5 minutes? Work? Okay. All right. Okay.